This lab is about estimating the excess charge on clear tape. The purpose of this lab is to explore the principle of electrostatic by preparing and analyzing charged pieces of clear tape. This experiment introduced the concept of charge and a fundamental property of matter. There are two physics principles. First is Coulomb's law, which is force equal to K multiplied by Q1 and Q2 divided by R squared. F is the electrostatic force between 2 point charges Q1 and Q2 separated by a distance R. K is the Coulomb's constant, which is 8.99 multiplied by 10 to the 9th. Another physics principle was gravitational force. Force of gravity equal to mass multiplied by gravity, which is 9.81. In this experiment, charged tapes are prepared by quickly separating two pieces of tape which transfer electrons and result in one piece having an excess charge. The fundamental physical principles involved include the conservation of charge and the nature of electrostatic force. A brief preview is that we will determine the approximate amount of excess charge on a piece of tape by measuring the force between the two charged tapes and balancing it with gravitational force. In this lab, we use clear tape, smooth surface, and ruler. Also, we could identify tape B and A as a system, and then surroundings were the desk and the air. And then we used this equation for estimating the charges, and the computational model assumed point charges located at the center of each tape and equal charges on both tape. So our initial condition was tapes were assumed to be initially neutral, and the charges were introduced by separating the tapes quickly, which transfer electrons. So our assumption was each U tape has the same net charge, and the charges were considered to be concentrated at the single point. Here's our execution from the lab. The length of the tape was 20 centimeters, its mass was 0.2 gram, and then the distance between tape B and A was 1 centimeter. The force of the gravity was 0.00196 Newton, and then the force of the electrostatic force was 3.83 e to the negative 23 Coulomb. Here are the magnitude of the charges. For the single charge was 1.48 e to the negative 8 Coulomb, and for the line charge was 1.04 e to the negative 9 Coulomb. So we assume that the total charge on tape is evenly distributed across its strength. So, and then we were questioned that what if the signs were reversed? In this case, it will still attract each other since they have different signs, but with the reversed charges. It's due to the different approximation and the distribution in each model, and it's considered only the primary electric force interaction between charges on opposite tapes. And then we're also comparing between the point charge model and the line charge model, and then we were able to conclude the line charge model is more accurate. Here are the more codes for this lab. So first of all, we set up the physical constant, and then here are the electric field, creating a function for the electric field, and then from this we start the part 1. So here are the position, and then creating the point charges, and then here are the calculating electric force and field. Then this part was given from the stutters, and then here are these codes for calculating the electric force and field. And then finally, we execute it by printing it. So if we're gonna compare data and then the prediction, the difference between them can be attributed to experimental errors or simplification in this model. So it could cause some of the errors such as measurement or environmental factors. Through this lab, we successfully estimate the amount of excess charge on a piece of clear tape by measuring the force between two charged tapes and balancing it with the gravitational force. This experiment demonstrated that everyday object can carry significant amount of charge, producing electrostatic force. This experiment reinforced our understanding of electrostatic principles and provided particular insight into the design and the data analysis. This key takeaway is that even simple household objects can exhibit complex electrostatic behavior, and careful experimental techniques were crucial for accurate measurement for energy.